The goal of technology for mathematical argumentation, or TMA, was to construct a computational environment in which elementary students could explore the behavior of arithmetic operations such as multiplication and division. It is based on the work of Russell, Shifter, and Bastable, who argue that investigating generalizations about the behavior of the operations strengthens students' understanding of computation and prepares them for formal algebra. The authors introduced the idea of representation-based proofs, a way for young students to demonstrate why a generalization is true, using a representation rather than algebraic symbols. Such proofs involve a representation of a quantity, some change in that representation that represents the operation, and a recognition that the resulting representation is still the same quantity. In this example, students are coming to the generalization: given two addends, if some number is subtracted from one addend and the same number is added to the other, the sum remains the same. Our system, Classroom Learning Partner, provides two kinds of tools to support this process: tools to construct and manipulate mathematical representations, such as arrays, which can be changed to have one undefined dimension, which we called fuzzy arrays, and an animation system to record the transformation of a quantity through an operation. We designed a curriculum sequence to lead second grade students to explore the generalization n times 4 equals n times 2 times 2, or multiplying a number by 4 is the same as doubling it, then doubling it again. We first introduced students to the animation tools and the tools for creating an array, cutting an array into smaller arrays, rearranging arrays on the screen, and snapping arrays together to create a larger array. Students then explored a sequence of specific instances of the target generalization using the array tools. 5 times 4 equals 5 times 2 times 2. 7 times 4 equals 7 times 2 times 2. And 9 times 4 equals 9 times 2 times 2. Students solve these problems in a variety of ways, such as by snapping two 5x2 arrays together to show that they are the same as a 5x4 array, or cutting apart a 7x4 array to show that it is the same as two 7x2 arrays. We then discuss whether they thought this statement would be true for all numbers, introduced the idea of n to mean any number you can think of, and demonstrated how they could modify a specific array by using the hide rows or hide columns commands. With the rows or columns hidden, an array becomes a fuzzy array, an array with an indeterminate number of rows or columns. Students explored the generalization in a variety of ways. Some created a specific array, made it into an n×4 array, then cut it into two n×2 arrays. Others cut a specific array in half, then snapped it back together before making it into an n×4 array. Some students were able to go beyond the targeted generalization to the variation n times 6 equals n times 3 times 2, while these second graders showed a remarkable ability to grasp the idea of a generalization. Some of them found the fuzzy array confusing. As a result, we redesigned the array to allow students to enter n instead of a specific number as one of the dimensions. Grid lines do not show in the n or hidden dimension. TMA is a collaboration between MIT and TERC. This material is based upon work supported by the National Science Foundation.